some uh, thin film edges like these dosimeters, which are used by radiation workers, and in medical diagnosis like in CT scan, scintillation detectors are used to see the affected part in human body. And some X-ray scanners which are installed and the borders to check the smuggling of some dangerous materials. Okay, so my talk is divided into three major parts. So first of all, I will talk about radiation in general and radiation detectors, and I will also discuss how radiation interacts with matter and different type of radiation detectors. After that, uh, I will about the synthesis process to develop a radiation detector, especially scintillation detector, which is actually my area of interest. And finally, a very important part, which is the simulation part. This part is very important to detect new materials and also to study the properties of existing materials. So I will talk about a theory, famous theory, which is a density function theory, and also I will show some results like optimization process and band structure of materials, and on the basis of band structure. Hello.
जी 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 सर सर ओके वी आर लिसनिंग टू यू वी आर लिसनिंग
Oh, okay, sir. So yeah, please let me know if there are any questions or any if you need any clarification. So I want this session to be more interactive because in online sessions, just like if there is no response, then it's like you are forgetting on your laptop. So I want some feedback from my audience.
ओके
Okay. So let me broadly define radiation. Radiation is actually an energy. So this energy can be taken in the form of waves or
So
in the
WhatsApp
form of subatomic particles.
WhatsApp link achieve.
And uh, actually, I will talk about that type of radiation which has enough energy to ionize matter because for reaction purpose, only that energy, that type of radiation is important which has enough energy to knock out electrons from the matter. And on the basis of
Stream यार
that,
आता
we can
है अपलोड माइन तो लॉग आउट करे
detect radiation. So broadly, we define, we categorize radiation
फेसबुक पे हलियो
into major
हिकिड़ो
parts.
यूट्यूब चैनल ते हलाए छॾियो
Charge radiation
ठीकु
and
आहे हिकिड़ो मां
uncharged
हिन खे लॉग
radiation,
आउट करियां
and charge radiation is then further
मैं
divided
को लोग के
into
भले ना बने
light charge
न
particles
ही बि
and heavy
व्हाट्सएप
charge particles. So light charge particles are electrons and particles, and heavy charge particles are like proton and
मैंने जो
neutron.
बोला वो अपने ग्रुप में तो दे दे
And uncharged radiation
देखो फेसबुक जो तव्हां रखियो आहे न उन ते
two types: neutrons
लाइव
and
था लोग पढ़े
magnetic radiation. Electromagnetic
हिकिड़ो
radiation.
लाइव आहे
Actually, electromagnetic spectrum is very broad, but I will especially I will talk about X-rays and gamma rays. Actually, uh, these are radiation which have enough energy to Okay, okay. Now you can see me there. Okay, okay, sir. So let me
offer the stream
हेलो, अब वहां पे सही है? हेलो, हाँ, अब जी, अब सही है? ओके सर, ओके। सर, अभी ठीक है? आप मेरी आवाज सही प्रॉपरली सुन रहे हैं? Okay, okay. So even we can have some questions if you want, because I want this session to be interactive as much as possible. So if there are some quick questions we can have. Okay, so as one can see this peak, which is a photo peak coming from the photoelectric effect, and it tells us the energy, the total energy of the incident radiation. We actually used a source of radiation in our laboratory, that was cesium-137. We already knew the energy of that radiation, so we used that energy to check our detector. And the next thing is how much light this detector can produce, and we call it absolute light yield. So it is a very important parameter in assessing the quality of our detector. So it should produce as much photons as possible to detect radiation. So if this yield is better, then it it's one of the parameter to decide whether this detector can be used even at commercial level. And then we check the timing characteristic of our detector. This characteristic is very important. This actually tells us that for how long this detection or this interaction process is there. So we want our detector to be very quick, because in real environment, radiation is coming very quickly. There is a very small gap in terms of time. There is a very small gap. So we want our detector to be very quick. It should quickly come to its to the state where it is available for the next detection. So we found that the timing characteristic of these detectors is about 200 nanoseconds. So it is very quick. So after 200 nanoseconds, this detector is available for next detection. And even we checked how neutron can be detected using this detector. So when we used a source of neutron, then we saw a very clear peak about 3 mega electron volt. So it shows that our detector is sensitive for neutron detection as well. There is another important thing in the first, I think in the second slide, I have shown thin film badges which are used by radiation workers. Those badges are called dosimeters. So those dosimeters are used by radiation workers for a certain range of time, and it tells how much exposure those workers are getting during a certain time. So, for example, these badges are checked every like few months or 6 months, and if the dose is issued by them is very high, then either they can be replaced or they can go on leave. So so it actually helps us in knowing how much dose they are getting. So we also check the dosimetric properties of our detectors, and they work really well. And we can these peaks are showing that energy can be stored in the energy of the radiation can be stored very well. And whenever we heat our material, then that energy is released back. Okay, now the final part of my presentation, which is very important. This is actually independent from this entire growth and characterization part, but it is very important in predicting future materials for radiation detection, as well as these simulation studies are very helpful in theoretically understanding the processes which are happening inside our detector. So there are different approaches. One of the approach which we are using is density functional theory. So this is actually a technique to solve the quantum behavior of atoms and molecules. Actually, using quantum mechanics, we can get information about the quantum behavior of atoms and molecules, but that is very computationally that is very costly, because the system is actually not a single body problem. It's a many body problem. Many particles are interacting at the same time. So this method was developed to solve the complexity of applying Schrodinger equation to materials, and using this method we can solve the materials and their quantum mechanical properties in a very simple way. We actually use, instead of wave function, we use electron density to solve the certain quantum mechanical equations to finally get the properties of those materials. So the underlying principle of density functional theory is we use electron density, and instead of wave function we use electron density of the material to find material properties. So this figure shows that there are many interacting electrons, but we replace those interacting electrons with the electron density, and we can get same information in a very quick way using density functional theory. There are different packages which can be used to solve these quantum mechanical equations using electron density. But we have chosen Win2K because it's for us it was easily accessible, and there are other free packages as well. For example, this Quantum Espresso is the free package, and many researchers are using that package. But for our investigations, we pick Win2K package. And some of the results are published. For example, we studied thallium-based materials, and these materials are very attractive for detection of X-rays and gamma rays. So they have very simple structure. The structure is a cubic structure, and then we okay. The first step in applying the density functional theory approach is always to check whether this material is stable or not. We call it optimization. So during optimization, we check if this material is synthesized in laboratory, then whether it can be formed or not. So we found that these materials can be easily optimized at certain elastic constants, and elastic constant for each material is given as you can see. So this is always the first step to check whether it is possible to synthesize a material or not. So this is particularly important for predicting future materials. And next step is to check what kind of material it is in terms of the nature, like whether it's an insulator, semiconductor, or metal. So next we calculate band structure. So band structure calculation gives us information about the type of the material, the band gap, as well as the direct or indirect nature. So if material is direct, it means that electrons can easily make transition from valence to conduction band. And if it is indirect, then materials it is difficult to make transition from valence to conduction band. And next is the electron density. This actually tells us which orbitals are contributing in valence and conduction band. So I have shown the states for different compounds, and one can see that, for example, in the first material, that is thallium calcium fluoride, we can see that valence band is dominated by p orbitals, which are contributed by fluorine, and the conduction band is dominated by thallium atom, and the dominant states are states from the s orbital. Okay, so now I want to conclude my presentation. Actually, I talk about three different things. One was very fundamental about the radiation and radiation detectors. Then next, I talked about the material synthesis and how materials can be grown to make detectors out of those materials. And then finally, the simulation studies, which are very helpful in understanding the properties of materials. Actually, the simulation studies can predict future materials which are more efficient, and also these studies can be used to understand the properties of materials theoretically. So radiation detectors, they are often used in the form of single crystal, although there are many methods. So, but I talked about scintillation method. So it's a popular method of radiation detection. Simulation helps us in designing new materials and predicting their properties. There are many ways to synthesize or grow crystals, and it totally depends upon the nature of the material. For example, if it is toxic, then we cannot use Czochralski technique. If it is hygroscopic, then hygroscopic or toxic, we need to use Bridgman method. And if our preference is the quality of the crystal, then we prefer Czochralski method. There are some challenges. Crystal growth is very hard and it takes a long time to find an optimized recipe. But the good thing is these high quality crystals, as you have seen in my slides, they look very beautiful, although it's not a scientific reason, it's just for the aesthetic sense. But the best thing is once high quality crystals are available, then we are able to extract high quality scientific results. So I say thank you to everybody who is listening. And now, if there are any questions, then we can discuss. Thank you, sir. Thank you. Okay, sir. So I think there are some common grounds between us we can work on. As your department is metallurgy and materials department. Yes, sir. So now I think my work is as from this presentation, you may have an idea that this work is very closely related with your department. I don't know what kind of facilities you are having right now in your laboratories. Are the availability of materials, are different techniques for the synthesis you have. So once we know about those facilities, then we can work on synthesizing new materials, the investigation of some existing promising materials, as well as we can collaborate on the simulation studies for investigating some properties which are related to applications like radiation detection, or if you are working on are interested on some other applications, then we can tune accordingly to shift our interest in that side. Thank you, sir. It was really an honor for me. And although, as you mentioned, that there were some limitations, but this is part of the life. And overall, it was really wonderful to interact with you and your faculty members, your students. And I hope that we will continue our this linkage and cooperation in the future, inshallah. Allah Hafiz.